Tēnā koutou katoa. In 2001, when, believe it or not, I was as young as some of you, I had the pleasure of traveling to Sweden. And I went there as one of the teachers for a postgrad course on modeling, and I met a person named Joe Landsberg, whom some of you will be familiar with. Now, Joe had as his mission in life, he wanted to replace growth and yield modeling with physiologically based modeling, with models that had a higher level of detail. And so you can imagine, for a relatively young person, not just 9 years out from a PhD, when I got up to present and I started presenting my work, he stopped me in the middle of my talk. He stood up and he said, "Stop, I can't stand to hear anymore." And by the way, Russell, you did lock the door, right? Good, okay, good. Just in case you're thinking of running off now. But anyway, so we had an argument, and it was a really enjoyable argument. And we delved into all sorts of things, and we became friends as a result of this argument. We discussed such things as, well, from a philosophy of science point of view, should you start with an idea and then gather data to try and falsify that idea? Or should you start with a massive data set and try and get the data set to tell you what you should think about the way the system works? Or something in between? Or how detailed should a model be? And what are the consequences of having a very detailed model as opposed to a relatively simple model? And we talked about error propagation and the consequences of certain types of models and their error propagation in front of a bunch of now rather wide-eyed postgrads. But, and it's the error propagation that I wanted to focus on because it set me thinking, that conversation. And I started to think, well, if we wanted to bring physiology into mensuration, how would we do it without propagating and generating compounded errors, which is a feature of the kinds of models that Joe proposes. And so there's nothing on the screen. So I'm sorry, I'm going to have to look around from time to time. The overview of this talk is, what are we doing? How is it useful? How is it different from what other people are doing? I'm going to talk a bit about estimating productivity, estimating factors limiting productivity, and then hybrid physiological mensurational modeling. Thank you. Okay. So what are we doing? Well, we're finding ways to bring tree physiology into a mensurational context. And we're doing this through looking at constraints on the use of radiation. So things like temperature, soil moisture, vapor pressure deficit, nutrition. These limit the ability of trees to use the radiation that they intercept. And then we would take a prediction across a large estate of productivity and calibrate it against permanent sample plot data. So we don't start with the data. We don't use fancy systems to try and get out of the data what we think the data is saying. We start with an idea, and then we generate a prediction, and then we try and falsify that prediction. And then the second thing we're doing is we're applying these ideas to growth and yield models that are a coherent mixture of physiology and mensuration. So why would we do this? Well, it helps us to distinguish site influences from silvicultural and genetic effects on productivity. When you measure a tree, you're not just measuring the productivity of the site. You're also measuring the consequences of the genetics of that tree, and you're measuring the consequences of silvicultural systems that are applied to that forest. And so if we focus on just the site influences, then that's great to be able to separate that out. We can show which site factors are limiting growth. So we don't just have a layer that shows the productivity across an estate. We can show what's influencing that productivity, what the limitations actually are. We can provide estimates of current and future crop dimensions. And we can represent impacts of things like climate change or represent impacts of site preparation on final crop dimensions. So how do our methods differ from other hybrid modeling methods, because there's a lot of hybrid physiological and mensurational modeling that's happening around the world. And they come, in my view, into two broad groups. There are some groups who use very simplified but still quite complicated physiological models, such as 3PG, Kabbalah, SNW, that sort of thing. And these are, although they're lovely physiological models, from a mensurational point of view, they're built to generate errors. They're built to compound errors. They're built to accumulate errors. And you can see that immediately if you're a mensurationist. Others run ecophysiological models in parallel with growth and yield models, and they use physiology to adjust the coefficients and try and get the two models to talk to each other in a way. Well, we use ecophysiology in the first instance at the request of the companies who are involved in this project to predict productivity indices. And then we run mensurational models, or they presumably run mensurational models using those indices. But we're moving to fully integrated growth and yield hybrid models that don't accumulate errors, that we've retained the mensurational principles. Most critical of those is what's called path invariance, that cause the system to not generate errors. And we include physiology only when it's justifiable, when we can prove that it does some work. So we don't retain complexity. We make things as simple as possible. So how do we do it? Well, we assemble and localize topographic, climatic, and soil inputs. We run the physiological model at points across the landscapes, usually for a period of about 10 years, with 10 years of climatic data, to predict productivity. And then we test our predictions of productivity against permanent sample plot estimates of site index. And then we deliver high-resolution rasters to our partners, our industry partners, of estimated site index. And we also deliver some other layers, some rasters, GIS. I'm assuming you all know what GIS rasters are. They're like giant matrices that represent points in space, and at each point in the matrix you can have a number, and that number could be, for instance, a site index. And we also have rasters that show what's limiting productivity across the state. So let's see an example. This is for Kangaroo timberlands. And just to give you an idea of the sort of data that we use, for climatic data, we use what's called the Virtual Climate Station Network from NIWA. And there are 166 points that we use for this estate. We've found ways to localize some of the data to make it more local than just the 5x5 kilometer grid that you can see here. And we have the weather from 1972 through to 2019. In fact, every day NIWA creates a new layer for all of New Zealand using this network. We also have soil maps. We have digital terrain models, hopefully LiDAR-based digital terrain models. And we can produce this sort of thing. This is a site index layer. It's got almost 10 million points on it. We've run the model for 10 years at each of those points. It's 15 by 15 meters. And our calibration standard error is about 1.65 meters for site index. To put that in context, if you do LiDAR measurements of trees and combine some other site inputs to get an estimate, you might get something like 1.4 meters for a standard error. So that's our sort of target. If we get to there, we'll be delighted. We're at 1.65 at the moment. But we can also say that this is the extent to which temperature is limiting productivity across this estate. So the greener it is, the less temperature is limiting productivity. We can say that on this estate, if you have any kind of slope, productivity is going to be a little bit higher, and the flat areas tend to be a little less productive. And so this is slope across the estate. We can show that vapor pressure deficit also influences productivity. And it's almost the inverse in some ways, but not completely. They're not perfectly correlated, of course, otherwise we wouldn't do this, but we can show that VPD adds information and that it influences stomatal closure and therefore the rates of CO2 influx into leaves and therefore photosynthetic rates. We can, from soil maps, we can show that this is soil pH, and we found that soil pH influences what's going on, and soil carbon-nitrogen ratio. And gratifyingly, these relationships between pH and CN ratio, when we first looked at them, are very, very loose correlations until we adopted textbook ideas about what should be happening. We applied those ideas, and we started to get really strong correlations between carbon-nitrogen ratio and pH and productivity. So then we can say, well, where in this forest may nutrients be limiting growth according to those two things? And thank you. I must be 5 minutes away. Is that right? Good. The green areas are where the growth is least limited by nutrition, and the other areas are where you might want to put in some fertilizing experiments. We did this in two ways, one using the old soil map systems that are in the fundamental soil layer, and then Congo Timberlands was kind enough to go and gather soils data from some of their PSPs and to actually do some analysis of those soils. So we kriged the results of their analyses and then used that to generate the same layer. And we got a very similar story, saying that down that bottom end of the forest, there's a zone where you should probably examine the consequences of adding fertilizer. When we've done this in other forests that are less flat than Congo is, we find that if we do a model without slope and aspect in it, then we get errors that are distributed around the model. So in a residual plot, I'm assuming most of you know what a residual plot is, the model goes through that horizontal line, and the errors are distributed around the horizontal line. We've plotted them against aspect here. The large circles represent high slope, the small circles represent almost no slope, and you can see as slope increases, we start to see patterns with aspect in our residuals. If we apply slope and aspect into our predictions of productivity, then we start to see landscape effects across the site. Okay, so that's all very well. We can create layers and we can show what might be limiting productivity. How about growth and yield models that are one coherent mixture of physiology and mensuration? Well, again, I'm going to show you some residuals. Now, some of you may or may not know this, but these are the kinds of residuals that make a statistician weep for joy. Okay, so when you statisticians, you probably look around, you can see who's weeping. Those are the statisticians. These are really nice sets of residuals, really nice normally distributed errors from a great mixture of predictions from just a couple of years predictions, some of them out to 30 years in this mixed data set for mixed intervals across a range of PSP data. And the very best mensurational model, the traditional model that we could find, what we call an augmented mensurational model that included elevation, for instance, to adjust the coefficients to make subtly different shapes and asymptotes for different models and different sites, gave us a standard error of 0.921, and our hybrid physiological model gives us 0.835. So for what I think is the first time we have found a method to incorporate physiology into a model in a way which will actually beat mensurational models. And that's new, right? Because if you compare 3PG, if you get Joe to parameterize 3PG, and you compare it with a mensurational model, for instance, in Canterbury, the mensurational model it beats it hands down. There's no comparison, right? So we've now got a combination of mensuration and physiology that is giving us some gain in prediction, which is exciting. So the main points are we're using tree physiology and to predict productivity. We calibrate with permanent sample plot estimates of site index. We have standard errors close to those obtained from directly measuring trees. Some of that error, of course, is the error of the site index model, which we can't avoid. And those errors typically run even within a plot, they'll run in the sort of up to 1 meter range. High resolution raster layers showing productivity across landscapes is one of the things we produce. We also have raster layers that illustrate the things that are likely limiting productivity. And we're now developing growth and yield modeling systems that use these techniques and currently the best fits I wouldn't say they always do, but they can be with physiological and mensurational hybrids. A lot depends on the quality of inputs you have. And I've been through some exercises where We've added aspects of physiology. We get an improvement, an improvement, improvement. Then we had the water balance model, and the model's worse than when we started because we're limited by inputs. We're limited by the quality of the inputs that go into these modeling systems. And often our soil inputs, the depth of the root zone, the texture of the soil is very poorly represented across landscapes in New Zealand. That's a big limitation. So I'd like to acknowledge people who are involved in this. So Forest Growers Levy Fund has contributed to this project. We're really pleased to have their contribution. Nelson Forest Management. Craig Brown is actually the first one who invited me to be involved directly with industry for this, and I'm really grateful for that, Craig. And Global Forest Partners Limited, Kind Timberlands Limited, Blakely Pacific, Juanita, Rayonier, NZ, the Swedish University of Agricultural Sciences, and then you can see my collaborators there, some really neat people who I really enjoy working with. So thank you to all of them as well. I've been asked, just one last thing, by Russell, does this have a future? It's a rather difficult question for a researcher, and the honest answer is I don't know. You know, it's exciting for a researcher, and it's new, and it's giving us what we think are gains, but there are costs as well. You need a greater range of inputs to run these models. You can ask more interesting questions of these models than you can with traditional growth and yield models, but we'll see. If it's worth enough to you to go ahead and gather or purchase the weather data and improve the soils data to run this sort of thing, then it has a future. If it's not worth enough to you, then it doesn't. And I don't know the answer to that question. So, thanks.